How would you maximize your calendar by removing the fewest overlapping meetings? Non-overlapping intervals is a Pattern Mastery 100 favorite and a go-to at Google, Meta, and Amazon to test your greedy reasoning with intervals. Over 30% of candidates make the wrong removal choice or miss the best sorting strategy. Nail this and you'll master scheduling and optimization problems in interviews. Let's break down non-overlapping intervals using the basic approach, a proven strategy for greedy interval problems. Given a set of intervals, start, end, find the minimum number of intervals to remove to make the rest of the intervals non-overlapping. List of intervals, unsorted, may overlap. Integer, minimum number of intervals to remove. Think of cleaning up an overloaded meeting calendar. What's the smallest number of meetings you need to cancel so that no two overlap? Interviewers might ask, how do you optimize a schedule to fit as many appointments as possible without conflicts? What's tricky? Choosing which intervals to remove for minimal impact. A greedy approach, sorting by end time, works best. If you always pick the interval that ends earliest, you leave more space for future intervals. Classic greedy logic. Sort intervals by end time, not start. Initialize end to -infinity and count to 0. Loop through the intervals. If the current interval start is greater than equals previous end, keep it and update end. If not, remove it, increment count, since it overlaps with the last chosen interval. Let's clarify. You're maximizing the number of non-overlapping intervals, so removal count equals total, max non-overlapping. Sorting by end time ensures each choice leaves the most room for what comes next. Edge cases. No intervals or only one, return 0. All intervals overlap, remove all but one. Sort intervals by end time. Initialize end equals inf, count equals 0. For each interval. If interval.start greater than equals end, keep it, update end equals interval.end. Else, overlap, increment count, remove this interval. Return count. Let's try to implement it using solution 1. We start by creating a class called solution. This is just a container to hold our method. Inside our class, we define a function called erase overlap intervals. It takes in a list of intervals, where each interval looks like start, end. Our goal is to remove the minimum number of intervals so that no intervals overlap. First, we sort the intervals by their start time. This puts everything in order, like lining up tasks on a timeline so we can process them from earliest to latest. Sorting costs O(n) log n time. We store the number of intervals in n. Just a quick helper variable so we don't compute the length repeatedly. We create a DP array, where each entry starts as 1. Why 1? Because any single interval by itself forms a non-overlapping chain of length 1. This array will eventually store the longest chain of non-overlapping intervals ending at each index. This uses O(n) space. We also track a variable called max_chain to remember the largest non-overlapping chain we've seen so far. We loop through all intervals from left to right. This is the ending position of our chain. For each interval I, we compare it with all earlier intervals j. This double loop creates a time complexity of O(n², because we're comparing every pair. This conditional checks two things. Non-overlapping condition: if the end of interval j is less than or equal to the start of interval I, then interval j can come right before interval I in a chain. DP update condition: if taking interval j and then I creates a longer chain than what we have so far, we update it. If the chain improves, we update DPI to reflect the new longest chain ending at interval I. We also keep track of the largest chain found anywhere so far. This lets us compute the final answer later. At the end, we return the number of intervals to remove. Why n, max_chain? Because if the longest non-overlapping chain has max_chain intervals, then everything else must be removed. This turns our DP chain length into the minimum removal count. Solution 1. Test case 1. Let's test our function using this input. 1, 2, 2, 3, 3, 4, 1, 3. These pairs represent intervals on a timeline. Each one has a start and an endpoint. Here's why the solution works. We first sort the intervals. Then we try to build the longest chain of non-overlapping intervals. For this input, the best chain is 1, 2, 2, 3, 3, 4, which has length 3. Since we have 4 intervals total, that means we need to remove one interval, the one that overlaps too much. And that's exactly what our program outputs. 1. This confirms that our code is working correctly and passes the test. So, our implementation is correct. The algorithm successfully finds the minimum number of intervals to remove by computing the longest non-overlapping chain, efficient, accurate, and reliable. Let's try to implement it using solution 2. Overall time complexity. Sorting, O(n) log n single pass through the intervals, O(n). So the total time is dominated by the sort, O(n) log n, with O(1) extra space. We only keep a few variables. This line defines a class called solution. Nothing magical here, just the container for our code. Inside the class, we define a method called erase overlap intervals. It takes one argument, intervals, which is a list of start, end, pairs. Each pair represents a time interval on a line, and our goal is to remove as few intervals as possible so that no two overlap. Here we sort the intervals by their end time. So instead of looking at when intervals start, we care about when they finish. Why? Because this is a classic greedy trick. If you always pick the interval that ends earliest, you leave as much room as possible for future intervals. We initialize a counter called removals to 0. This will keep track of how many intervals we decide to remove because they overlap. Next, we set prev_n to -infinity. You can think of prev_n as the end time of the last interval we decided to keep. Starting with -infinity just means before we pick any interval, the timeline is completely empty. So the very first interval we see will always fit. Now we loop through every interval in the sorted list. For each interval, we unpack it into start and end. Here we check whether the current interval overlaps with the one we last kept. If start greater than equals prev_end, that means the current interval starts after or exactly when the previous one ends, so they do not overlap. If start less than prev_end, there is an overlap. So this condition is our overlap test. This comment is just explaining the happy path. When there's no overlap, we choose to keep this interval. In the no overlap case, we update prev_n to the end of this interval. That means we're officially accepting this interval into our non-overlapping set. And from now on, all future intervals must start at or after this new prev_end. If the if condition fails, meaning start less than prev_end, we land in the else block. That's the overlap case. This comment reminds us what we're doing in the else case. The current interval overlaps the last one we took, so we'll remove this one instead of breaking our chain of non-overlapping intervals. Because we sorted by end time, the current interval ends later or equal to the previous one, so it's always safe and optimal to remove the current one. Here we increment our removals counter by 1. We're saying this interval caused an overlap, so we're counting it as removed. We don't change prev_end in this case, because we're not keeping this interval. We're sticking with the previous one that ends earlier. Finally, we return removals. That number represents the minimum number of intervals we need to remove so that the remaining intervals are non-overlapping. And that's how this algorithm works. It first sorts all the intervals by their end time and initializes a running previous end marker, then greedily walks through the intervals, keeping non-overlapping ones and counting how many overlapping intervals must be removed. Efficient, simple, and elegant. Solution 2. Test case 2. Now testing with 1, 2, 1, 2, 1, 2. All of these intervals overlap completely. The greedy strategy keeps the interval that ends earliest and removes all others. Since only one interval can remain without overlapping, we must remove 2 of them. And that's exactly what our program outputs, 2. Perfect match with the expected behavior. So, our implementation is correct. The algorithm efficiently determines how many intervals must be removed to eliminate all overlaps. Simple, greedy, and highly effective. Quick recap time. We tackled the classic calendar cleanup problem. Remove the fewest intervals so the rest don't overlap. Breakdown recap. Conceptually, we're optimizing a schedule. From a pile of possibly overlapping intervals, we want the smallest number of deletions so what remains is conflict-free. Assess recap. We compared options and landed on a greedy strategy. Brute force is impractical here, but if we always keep the interval that ends earliest, we leave maximum room for everything after it. This directly maximizes the number of non-overlapping intervals and, by complement, minimizes removals. Structure recap. The plan was straightforward. Sort by end time, sweep once, and keep an interval only if it starts at or after the end of the last kept one. Every time we see an overlap, we count a removal. The final count is the minimum deletions required. Implement recap. We implemented this flow on LeetCode and the solution executed cleanly without any errors. Check recap. We verified the logic with LeetCode's runs. confirming that it behaves exactly as expected and passes the test cases, including edge scenarios. Key takeaway: when scheduling is involved, earliest finish first is a powerful greedy pattern. By maximizing what you can keep, you automatically minimize what you need to remove.